My name is Suresh Rajgopal, and my colleague here, Brent Byron, we're both from Micron Technology. And I know we are the last ones keeping you from lunch, so we're going to do our best to make sure we stay on track and you guys can get to lunch. So what we're talking about today is with the growing role of storage in the AI infrastructure, we wanted to talk about sort of the diverging needs that it's placing on SSD architecture. So there's a divergence in the requirements that SSD storage need to meet for some of the AI use cases. So what we've done is sort of separated this into two parts. I will be talking about what we're calling near GPU SSDs. So SSDs sort of on the north-south path of the GPUs, as well as cluster or near local SSDs across the network, while Brent will talk about capacity SSDs. And we'll talk a little bit about the workloads that are driving some of this, and then what type of SSD feature or architecture requirements do they drive, and therefore, what aspects of those architectures features should the SSDs optimize around. So that's effectively kind of how we break this down. So this figure shows sort of two training use cases where the near GPU SSDs kind of play a meaningful role in the compute cluster. As you can see, the first use case on training is fairly standard, where your data that's typically brought in and ingested gets cleaned and prepped and fed into a compute SSD. So there's an ingest phase, and then after that, you've got the data sets being fed to the GPUs for training. And the second use case is kind of the more common use case during training, when you're doing checkpointing, where the model state, the optimizer states, the model parameters all have to be saved to storage at some point. And the following requirements are the ones that we see as being predominantly important for storage to address. So, and we'll talk to each of these in greater detail. So sequential reads, sequential writes, high bandwidth support, being able to be power efficient while doing that, and then also a need to enable liquid cooled storage. So with the ability of supporting this kind of feature set, there are benefits overall to the system. So if you are able to perform some of these tasks faster, you get better utilization at the GPU level. If you're able to optimize power, you leave more power for the GPU to perform its task, and there's overall system TCO benefits also with that. Before we go into the individual requirements, there's another emerging use case that I wanted to touch on, and this is something that has been talked about in several talks, even this week at SDC, specifically KV cache reuse tiering during inference decode. As we know, during the inference, there's the prefill phase, which is compute bound, the decode phase, which is memory bound. And every generated token needs the previous KV cache in order to generate the next token. And so normally this is recomputed by the GPU, but in some cases it might be more efficient to cache it and restore it from a previous location. And this could typically be CPU memory, but as you can see, the growth in LLM inference is happening in two directions. There's batch sizes that are growing. More and more users are simultaneously querying the LLM model. So you've got KV cache context that needs to be maintained for each of those users. Secondly, the input sequence length and the output sequence length. So the length of that token is getting larger and larger. So that this again increases the KV cache size. So this is causing a spillover of that KV cache from GPU memory to CPU memory to near GPU storage and then on to network storage. And so that's driving requirements. And I don't have in this talk specifics on the data here, but just summarize some of what the transfers look like. They're typically, large writes that are happening for an entire layer, and so these end up being, 2 megabyte writes and then 20 to 32 kilobytes of reads. And these are growing as your context length grows, as your batch sizes grow. And then the ratio of, whether you do reads or writes depends on, the usage model on the LLM with respect to hit rates and how often users come on and off. Okay, so now talking about the drivers for near GPU storage, let's start with sequential write bandwidth. So the top figure on the left-hand side essentially shows PCIe sequential write bandwidth across generations, and this is fairly standard across most SSD providers. You're looking at 6 to 7 gigabytes in Gen 4, going all the way to 11 to 14 gigabytes on Gen 6. And the use case here with respect to checkpointing, you typically are saving away parameters and optimizer states. And as an example, a 405 billion parameter model will have a checkpointing size of about 11 terabytes. And the goal here is to try and make sure that you're checkpointing frequently enough that you do not have to roll back your state and waste GPU utilization. The other dimension to this is if you do checkpoint frequently enough, then you're spending more time checkpointing, and so the GPU is not doing useful work. Yesterday, Pratik from AMD presented material, and he had some fairly detailed breakdowns of what he called the fault tolerance stacks, which is essentially this trying to find this right balance between how frequently you checkpoint versus how much time you leave between the checkpoints. So this is an example that we put together where the assumption here is, okay, we're checkpointing. This is just an illustration saying we're checkpointing every 2 hours. And if you look at a certain percentage of time you want to spend checkpointing, anywhere from 1% to 10%, how long does it take to complete the checkpoint? And therefore, how much of data, what bandwidth do you need? And how can you service that with multiple PCIe SSDs? And clearly you can see that in this particular example, so if you look at, say, a checkpoint completion time of 360 seconds, about 6 minutes, with just 5% utilization of that 2-hour period, you can get the task done, with half the number of Gen 6 SSDs versus Gen 4. Another way to look at it is if you complete the checkpoint completion time with a Gen 6 SSD, you can do it in half the time. And so that has benefits because now you freed up more time at the GPU level. So another dimension to this would be to say that if you completed the checkpoint in 360 seconds versus 180 seconds, now you've improved the percentage of useful work that the GPU can do from 95% to 97%. So there's the benefit of increased sequential write bandwidth on the SSDs. Now let's look at the read side of the equation. Typically, when you do model training, you need, this is done on large clusters of GPUs, and to accelerate the training, various techniques are used. One of the techniques, specifically data parallelism, takes the model and replicates it across multiple instances of the GPU. So when you get to a stage where you're doing a checkpoint restore, what you've got to do is to have multiple readers restoring the checkpoint file back to the individual instances of the GPU. So now you've got significant sequential write bandwidth that has to be serviced, and until that restore happens and the GPUs synchronize, everything stalls. So the faster you can do that restore, the better it is. So if you look at that figure on the top right, it shows, again, PCIe SSD sequential read bandwidth over generation. So Gen 4 at 7-ish gigabytes per second, going all the way to 27, 28 gigabytes on Gen 6. So that same 11 terabyte checkpoint that we talked about, that if we take an example of saying, I want to complete that restore in 5 minutes, now obviously as you increase your parallelism instances, the bandwidth required to complete that and the number of checkpoint restore readers you need would change. And this example essentially is highlighting the fact that you can go from a 32 instance data parallelism to a 64 instance parallelism, keeping the same number of SSDs if you've switched from a Gen 5 to a Gen 6. So the higher sequential read bandwidth gives you that benefit. So these are two examples of bandwidth improvement that could help accelerate training tasks in the AI pipeline. I now want to switch to power efficiency. And, sorry, go ahead.
Did you also try with model parallelism?
With model parallelism, it's less of sequential reads that end up being the requirement. It's the writes become more important there to be able to accelerate. So it's sort of the dual of the data parallelism. So with respect to power efficiency, before I show some data on what the benefits of power efficiency are, I want to talk a little bit about this example that we collected the data on. This is an MLPerf storage benchmark called UNet3D. Essentially reads large image files into GPU memory, and then the training is performed on it to generate volume segments. And so what the storage sees here is there's the ingest phase of pulling in those large sequential writes to ingest the files. And then the training kicks off these large random reads to enable training. And typically this is a storage-bound benchmark, which is that until that read happens and is brought into the GPU memory, the training does not start. So again, a case where if you're able to accelerate that, there's more benefit in doing it. So if you look at this chart here, what we did was we ran the benchmark for about 1,500 seconds, and that's what you see on the x-axis. And the plot shows the power consumed during the course of the benchmark while it performs these two tasks. And the Gen 5 drive is shown in blue, and the Gen 6 drive, this is our Micron drive, that we recently announced, the plot shows in orange. And you can see there's the ingest phase where sequential writes come in, and then there's a read for training phase, which is where the random reads come in. And clearly the Gen 6 drive is consuming more power than the Gen 5 drive, but if you look at the amount of data that was ingested and read in, on the top right, you can see that the Gen 5 drive took about 1.1 terabytes ingested in that time frame. The Gen 6 drive was able to consume 3.6x more data while maintaining the same performance per watt. And similarly, for the reads for training, you've got almost 7.5x more reads being done by the Gen 6 drive with slightly better performance per watt. So it's not only important to run fast, but it's also important to do that power efficiently. And the benefit of that is you are able to do that with lesser power. You get the task done sooner. That when on a workload that's storage bound, that leaves time for the GPU to perform its task. One more comment on tracking power. This is the same workload where this is reporting power at the drive level. I wanted to call out a TP that Micron co-authored in NVMe called TP4199, which essentially provides the drive with the ability to track power during execution. So you can get total power consumed, total energy consumed, a power threshold can be reported, as well as a power histogram over time. And this plot is effectively showing in that range of 4.5 to 18.5 watts, it shows the different durations at which the drive operated in during a power window. And so this is certainly a very desirable feature for a drive to have, so that you can track power over time. The system can track how the drive operates across different applications and then optimize accordingly. Okay, finally, transition to liquid cooling. So the figure on the left shows a 2U server. This is very prevalent today, which has liquid cooled storage for the GPU and the memory, but you can notice that the storage configurations are still air cooled. So you still have fans set up for cooling the storage. When you transition to liquid cool, and that's the figure on the right, that shows a GB300 1U server with cold plate liquid cooled storage bay. Now, this has several benefits. Clearly, rack density is a benefit. You've removed these large fans, so you go from a 2U to a 1U, maybe even a 0.5U down the road. Secondly, you get lesser energy, less noise from the 20-watt fans versus going liquid cool. And lastly, there's greater efficiency because the air conductivity versus liquid cooled conductivity is much better as it goes through the cold plate. So this is certainly a direction for SSDs in the near GPU space to be paying attention to. Now, when we say liquid cooled, typically there's direct-to-chip or immersion cooling, and what I'm referring to here is direct-to-chip liquid cooling. And it's important to discuss what type of form factors make sense here. And in that space, it's typically either E1.S or E3.S. And the 5.9 millimeter really is not very conducive. There's no enclosure. The components have different heights. So it's not a very appropriate configuration for liquid cooling. But with the 9.5 millimeter, you'll see that you can consider having cold plates on both sides, cold plates on a single side, or cold plate on the connector end. And if you sort of grade some of the performance capability, from a thermal standpoint, having cold plates on both sides is beneficial to the drive, as well as the SSD design, but it poses challenges for serviceability. On the other side, the connector end cold plate doesn't do as well on the thermals, but it's easier on the host side. And so the single-sided is kind of somewhere in between. It's not perfect, but that's one of the areas that's potentially deployable in the near future with respect to being able to cool it. Puts some challenges on the SSD to be able to transfer the heat from the bottom side to the top side and be able to do that effectively. For E3, another scenario for, besides the both sides and the single side cold plate, there's also the option of putting the cold plate on the edge, but that has its own challenges. Most recently, there was a talk at OCP where various suppliers as well as OEMs talked about the different storage solutions here, and this is a place where standards could really play a role because there are some considerations that come in specifically with respect to the cold plate contact area, where the label is placed, what kind of flatness and roughness you have on the enclosure. Do you have a TIM or you do not have a TIM? So the thermal interface material. So these are all considerations that need to play in, but once we get to the stage, SSDs will be in a much better space to support some of the high requirements that compute clusters and AI pipelines require. Okay, so I will hand over to Brent now, and he can cover the capacity side.
All right. All right, this is your big SSDs for ingest and other uses. So you've got up in the top right kind of showing what we're prioritizing here. Capacity, obviously, but we need good bandwidth, and we need good power efficiency always. IOPS are a little less important in this case. So this might be into your QLC SSDs in some cases, but the kind of capacities we're talking about is 128 up to a petabyte. Maybe it'll go beyond this. Right now, there are ways to get to a petabyte. That's possible. NAND placements become a big issue. We'll talk about that a little bit. Obviously, power and the cost. Now, I'm going to focus a lot on the IU size and what that means to SSD design and how it's used with the host. So we have a DRAM budget challenge, Typically, 4K IU has been used. 16K is now in play in the industry, and it's getting more acceptance. It creates a challenge for us. We've got a graph here with quite a bit going on, but there's a yellow line on the top that basically shows the extra DRAM space that I have if I'm mapping with 4K units, and I have basically 1 GIB per terabyte of drive space. So on the 2 terabyte, no problem. You know, it keeps going like that up to 32. And then 64, if I keep that mapping unit the same size, I start to go into negative DRAM space. There's obviously the number of table entries in my mapping tables is doubling with the capacity. And that makes sense. But also the size of those entries is increasing a little bit as I have to address more NAND. And so now I'm running into the negative space. The 1 gigabyte per terabyte ratio can be broken on these larger capacities. That DRAM obviously presents a problem for PCB space. It is eating some of the power budget. We'll talk about that a little bit. That power budget that I'd prefer to put to the NAND to give you throughput. The signal integrity also becomes kind of an issue when you've got these large die stacks of DRAM and you're clamshelling them on a PCB. We may have to run the DRAM interface at a lower speed to support that for signal integrity, and that means we could potentially create another bottleneck for your performance that we do not want. We don't want the DRAM to be in that path. All right, so DRAM density, you know, the bits are not scaling the same as NAND. This is the trend. So the problem of fitting your tables into DRAM and fitting the DRAM onto the PCB, it's just going to get worse over time as these capacities get larger and larger. That's basically the only point here. Down at the bottom, I mentioned a 64K IU is on the horizon. It may be needed. So basically, let's talk about solutions to reducing the DRAM that we need on these big SSDs. So we could store the L to P table, that's the logical to physical table with the mappings. We could store that in the NAND instead of the DRAM, or cache pieces of it, things like that. That creates a QoS problem, and maybe that's okay for what you're using, maybe not. That's a bit more of a client SSD type solution. It's possible to do that though. We could change the L to P structures in a way where we sort of zone it into smaller segments in the drive, kind of like having different endurance groups internal to the drive. That creates a lot of complexity with firmware, and we have to wear level within those groups, etc. That can remove a few of those extra bits that get tacked on as we're addressing more NAND. That can help you probably up to 256 terabyte even, but you're still going to run into a space problem getting this DRAM on the PCB when you get up to 512 terabytes. So it's not a solution all the way through. Increasing the indirection unit size seems to be what's being aligned on. Obviously, that's not a perfect solution for every use case. It does increase your write amp if you're writing smaller than the IU size. And you may want to, when you're getting a drive that has a larger IU, you may want to see a spec of the endurance with that IU size, not just the standard JEDEC 4K workloads. That can become important to you to understand the endurance, especially with QLC where you get a few thousand cycles versus 10,000 plus program erase cycles on the NAND. So power budget, here's an example, 25 watt, 64 terabyte drive with two different IU sizes, 4K and 16K. So one necessitates a lot more DRAM. Here it's kind of extreme, it's 128 gigabytes of DRAM. That may actually be a real solution if you wanted to keep the 4K mapping because you need to match the sizes and the way the units are bought and placed on the drive. But it's pretty extreme. So you got 128 gigabytes of DRAM versus 16. And it's showing relatively the kind of budget you're eating in your power. I've only got 25 watts and I'm using all of it. I would prefer that more of it goes to the NAND so I can activate more die simultaneously. 1 or 2 watts makes a huge difference here in your throughput. You can see down on the bottom the comparison of the two. Again, pretty extreme example, but you can see how this is a big deal. So less DRAM that I'm actively using means more NAND. Now, when you're getting more throughput, you're bumping the power up on the controller a little bit, things like that, but it comes out as a net win. Now, there's impacts for having larger IU size. Reads can be impacted in some cases if the IU were bigger than the NAND page size. That's possible, but really we're talking about writes here and write amplification. So we've got a graph here that shows the IU-induced write amplification, meaning it's not just the amplification you get from doing random writes, but there's more just because you're doing host writes that are smaller than the drive's internal direction unit. So if you've got a 16K IU and you're doing 4K transfers, you can be adding 4 to your write amp. That's a pretty big deal. That's on top of your normal write amp. As the size gets bigger, it's better. You'll see that the purple line is if they're aligned, if those writes are aligned to your IU. And the black line, or dark blue above it, is if they're not aligned to it. But as the sizes of the transfers gets bigger, the extra write amp from the IU mismatch gets better, even if they're unaligned. So aggregating and issuing large writes is a good idea. Lots of small writes, which you may not always be able to control. But you're going to be eating your endurance, and you're also going to have performance issues if you're doing that. Now, size matters. Like I said, bigger is better if you're doing writes. If you're unaligned to your IU, but you're doing a very large write, everything in the middle is intrinsically IU aligned, which means you're only getting damage from the head and tail. And you saw that in the way the graph looked above with the unaligned writes. So as it gets bigger, the impact of that extra write amp is less and less. Something to consider in the way we're using these drives. All right, briefly, and I think this has been covered in other places here, Anthony Constantine from Micron covered the E2 form factor. But basically, we're having trouble fitting all the parts we need on gigantic drives like this. You can see there's 64 NAND placements here on this E2 512 terabyte drive. Obviously, you can increase the NAND die stacks, so you can have up to 32 in each package. That has its own drawbacks. Similar to the DRAM, you may run into having to run the NAND interface at a lower speed to support that for signal integrity and other problems like that. But here I am using up all this space with the NAND, even on this new form factor, and I've still got those yellow boxes there. Those are my hold-up caps. That may increase. The amount of throughput you want may cause me to need more hold-up caps. I've got to have space for those. I've got to have space for all that DRAM, so the IU size becomes a necessity to go up in IU size so I can fit the DRAM on there along with all these other parts. So that's why new form factors may need to be considered here if you want to go into these very large capacities up to a petabyte. Just a few more examples. I think this comes from Anthony's presentation actually, but you're talking thousands of NAND die, thousands of them on here. So yeah, with regards to the NAND packages having 32 die in there, that's probably the limit. We can't keep increasing the Z height. So we can't go to 64 very likely, maybe in some future, but we'd have to make even a thicker form factor if we go over that Z height. So 32 is probably your limit. And basically it's showing a few different options that you could get up to the 512 terabyte. Petabyte, maybe not so much unless you're in the E2. So just to conclude here, the AI use cases are driving different storage requirements. So you've got the near GPU SSDs, you've got the high capacity ones for ingest. These could be different kinds of SSDs. SLC, TLC on the first maybe, and up to QLC on the capacity, depending on what performance you need for those. And both need to be power efficient. And by power efficient at the SSD design level, I mean diverting as much of the power budget I have to the NAND so I can activate more dice and give you better performance. That is the end of our presentation. Thanks. Yep.
Are you looking at liquid cooling for the capacity SSDs?
Yeah, right now, sorry, repeat the question before answering. Yeah, are you looking at liquid cooling for capacity SSDs was the question. And no, right now there does not seem to be an ask there, and part of that is probably going to be driven by the server manufacturers who actually need to make sure they're plumbed for that, but at the moment, no. Question in the back?
Thank you. My question is, have you considered a microcontroller which has the DRAM dies in the package? Because I see that there are 3 benefits coming out of it. One, use the space which is in the package in the 3-dimensional space. Right now, if you place the DRAM next to the microcontroller or the controller, you are in a 2D planar space. But when you start stacking the dies, you start using the Z heights inside the package. So that's one benefit. Power is definitely the second one because there's a lot of energy loss when you move from package to package and traces. And the third one is signal integrity. So if you move the DRAM within the package of a controller, you have lots of benefits. However, there is one problem I can see is the package size becomes bigger. So have you considered all these options for your next controller?
So hopefully everyone heard the question. I'll just rephrase it. I think the question was, have you considered accommodating a controller? And I assume here the controller you're referring to is not just the DRAM controller, but the entire SSD controller alongside the DRAM die resident on the same package. I think from a benefit standpoint, that's certainly all the benefits you pointed out, despite the increased package size, which needs to be fit on the PCB, signal integrity benefits, potential thermal benefits are certainly there. I think the challenge is really economics. Being able to manage, if there is a demand for that kind of a configuration, then I think it'll happen. But today, no. True. Other questions? I'm going to try and repeat the question. Is there you said a difference in hardware with respect to efficiency?
No, like with respect to everything that you spoke about, is there a hardware specific preference for any particular kind of SSD? Like for the capacity higher and for the ones that are near GPU?
But when you say hardware preference, I'm assuming you mean like the form factor or the configuration of the SSDs. Typically, that's driven by multiple factors. So the near GPU SSDs, they need to be very performant. They need to be able to cool better, and they need to be slim and small, which is kind of why there's a tendency to move to something like an E1.S. The capacity SSDs, as Brent called out, need to be capable of accommodating multiple NAND die, and so the hardware preference there is more towards an E3 or potentially even the new E2 form factor. So that's where the hardware trends go for the SSDs themselves. And then of course there's also how they fit in the server, whether they go multiple drives on a 2U, or they get slotted individually. Those are also factors that come in. Okay, thank you very much.